Welcome everyone to the most awaited webinar on mastering image similarity with Siamese neural networks. And our amazing speaker for today is Amedeo Biolatti. Amedeo has over 6.5 years of experience in the field of data science. And he's served in companies like PowerFleet. He's currently serving in PowerFleet as a senior data scientist. And he's worked at Swiss Re as a data scientist and similar roles in Evo Pricing, Intesa San Paulo. Apart from that, Amedeo has personally worked on several open source projects, and something that he loves doing apart from work is extensive research, right, in the field of data science. Apart from this, Amedeo's diverse background working in all of these different industries makes him the perfect guide to explore this fascinating world of image similarity using Siamese neural networks. So get ready for a very insightful session, and I'd hand over the virtual stage to Amedeo. Amedeo, all over to you.
Okay, thank you. I would like to start warming up a bit with a little quiz about Siamese neural networks. So I would like to ask you if you know why they are called in this way. The first possibility in this quiz is because they share the same structure. The second is because the original author of the first paper did really like cats. And the third one is because they share the same weights, so the same parameters. Maybe we can give a few seconds to answer. Okay, and maybe we can see the results. Let's say in that question, I think there are not really wrong answer, but there is one that is really correct, one that is so and so, and one that is, let's say, something more of a personal type of information that I don't know if it's available, but could also be true.
Can you see the poll, Amedeo?
So,
can you see the...
Yeah,
okay.
I can see it.
Okay.
Yeah, I can think we can see the results. I don't know if I can show the results on screen.
Can I end the poll now?
Yeah, I think we can end the poll.
I will be sharing the results.
Okay, let's say a few people like the, let's say, more personal answer. They really like cats, and maybe that's possible, but I don't think they call this model in this way for this very reason. The first one is the same, correct, since they share the same structure, but does not capture all the things that are important about Siamese neural network. And the third one is the one that is, let's say, correct and get more information available. In fact, as we will see, the Siamese neural network are called in this way. We could also call them twin, but let's see, historically they are called Siamese because they are two or more exact copy of the same neural network. So they have the same structure and the same weights. So now that we have warmed up a bit, we can start with let's say, brief PowerPoint presentation about an introduction to Siamese neural network, just to get to, let's say, know a few basic facts and few basic reasons of why we want to use them. And after this first part, we will get hands-on on the code and we'll try to code everything together from scratch. As I said, I'm Amedeo Biolatti, and this talk will be all about Siamese neural networks. First introduction. Why can we use the Siamese neural network? In general, the main reason is to get some, let's say, information about the similarity about two objects. The most common case is for images. We want to get some, let's say, sense of distance in the meaning of the image. So, for example, in thinking about possible applications, we can think about face recognition. So, for example, if we want to see if two photos contains the face of the same person, we can do that. It's common use of that kind of application for security reason in many kinds of companies, or also in many phones to, let's say, categorize your photos by the person that is, let's say, represented in this picture. But we could also use it for signature verification, for example, to check if two signatures are from the same person. For product retrieval, for example, if we have something like an image of an item, some kind, let's say, a power of shoes, and we want to look in a big data set of images for something that is somewhat similar, we can do that with that kind of algorithm, since it can give a degree of similarity, so we can get more similar shoes and very dissimilar ones, but we can, let's say, tune them in different ways. We don't have to, let's say, abide to a predefined concept of distance. We can define a new, our specific concept of distance in this application, depending on how we train the model. So, for example, we could look for similarity in, let's say, the color, similarity in the shape, or something in between. It all depends on how we do train this model. And also, this let us to build a cluster of similar objects, since let's say, a group of items that are similar between each other is something like a cluster. And also we can use it for some kind of classification when the number of classes is not really known before the training. So, for example, we can think, for example, at face recognition, something like that, something like a classification problem where we have many different classes and each person is a different class. But we will get at, let's say, prediction time. So after we have trained our model, new classes or new people to, let's say, classify. And this gets us to the first question. Why can't we simply use a classifier, some, let's say, classical, let's say, image classification algorithm to simply, let's say, divide the people by, let's say, this is a photo of Amedeo, this is a photo of, I don't know, someone else, and etc., etc. Because we don't know all the classes before training. We do not have all the information about how many classes and which classes we will have before we start training. For example, if we want to train something to classify the photos in our phone, depending on the person that is inside this image, we cannot do that because we don't have images and photos of every person on Earth. So we need something that can handle new, let's say, new similarity between new objects that we haven't seen before. Also, maybe in some application, we want some fine-grained definition of distance. We don't simply want to say these are the same thing and these are different things. Maybe we want some degree in between. So, for example, talking about shoes, maybe we have two pair of shoes that are really identical, so the same model and the same color. Another couple that is the same model but a different color, or a different color but the same model, and so on and so on. And maybe we go to very distant images where in one we have a pair of shoes and in another one we have a hat or something like that. So we have all these degree from very, very, very similar to very, very, very different, and all the in between that in general classifiers cannot really handle that well. And also, again, related a bit to the first one, maybe we don't have that much information about each class. So maybe we have just a few photos of a person, maybe 2 or 3 photos, even if we know that we have these persons. So we cannot really have, let's say, 10,000 different classes for 10,000 different people, even if we know all the people in our training, and we will never add new people to the face recognition algorithm we want to build. So we need something that has more, let's say, less strict about the number of classes, definition of similarity that can handle more a nuanced definition of it. Then we can think about, well, we can simply use a concept of distance in the between our objects. So maybe why something like the Euclidean distance, that is simply, let's say, the most simple geometric idea of distance. We can simply use that on our images, on our objects, etc., and get the, let's say, distance that we want to use. Well, that is, let's say, we could try with that. Maybe in some cases it could work, but it will not work in general, because the Euclidean distance do simply compare two objects or images, in our case, in a point-wise way. So it will ignore completely how the information is spatially distributed, and it will only look at one pixel at time. This is not very useful for images. For example, I don't care that the pixel number 37 is green if all the others are of, let's say, very different. Maybe it's simply noise. Maybe it's simply, I don't know, maybe it's a leaf in a, let's say, photo about a tree, or maybe it's, let's say, a hat in a photo about garment, or a person, or maybe a pair of glasses or something like that. I don't get any information from the fact that the pixel number 37 is green. I need the context where this information is. I need the spatial structure. And also another problem, if I take two images of the same subject, but of different sizes, maybe one is a very high resolution image and the other one is a bit less high resolution, so they have different sides, I cannot compute the Euclidean distance in any way because they have a different number of pixels. So I cannot find a, let's say, direct way to make a comparison. For example, here in this slide, we have a small example where we have these two pairs of images. In the first row, we can see we have a red column in vertical in, let's say, a slightly different position, and we get an Euclidean distance that is higher than 2, 2.8, 2, etc., etc. While if we remove the column completely, we get a distance of 2. This is because, again, the Euclidean distance is defined in a pointwise matter. So it doesn't really matter to this definition of distance that we as humans see the first two images as more similar than the other pair, because again, it doesn't matter the context, it doesn't matter the spatial distribution, and it's not robust in any way to many kind of transformation that maintain the meaning of the image, like translation, rotation, changes in the number, let's say, in the resolution of the image, etc. This is also true for any other kind of, let's say, complex data. So, for example, also for speech information, for time series, for many kind of data that are not well defined in a vector space in a unique way. So if we have many, let's say, kind of invariant transformation, different resolution, complex structure, etc., or maybe also discontinuity, any kind of complexity in the data, our original concept of Euclidean distance will probably not work well. So we can use a Siamese neural network. The idea is in reality quite simple in itself, and is to use a neural network to encode our complex object in an embedding, a vector representation. So we will compress our image in a vector of numbers that we will try to let's say, put in a way such that the Euclidean distance is then the Euclidean distance, or some other concept, more, let's say, easily defined concept of distance, is more aligned with what we want from that concept, let's say, from our complexity model. So we can see that we have an image on the left, and we put it inside the neural network. In our case, it's a convolutional neural network, since we are using images. So this convolutional neural network will flatten the image inside this one-dimensional vector of numbers. We can imagine it like something like 3.5, 2, -3, 25, 1, 1.9, etc., etc. And the same will be done with the other image. So we will get two vectors of numbers, and then we will compute the distance between these two. And this could simply be maybe something like the Euclidean distance, the angular distance, or any other concept of distance. Generally, the Euclidean distance is used because it's simpler, and let's say we will train our model to give a representation that works well with that definition of distance. It's important to note about what we said in the quiz at the start, that these two models are in reality the same. They share the same structure and the same parameter. Since, let's say, we want to use the same, we can call translation from an image to a vector. In this way, if we compute the distance of the same image, we will get exactly the same representation and a distance of 0. But we also want to be able to get similar representation if we give similar images. Clearly, at the start, when the model, the neural network is not trained yet, maybe we won't get something that is that performing on that, let's say, in that. Maybe so similar images will get different representation, but we will try to train them to get very close. Oftentimes, you can, in many cases, if you want a first implementation of this, you can simply take a pre-trained neural network. You can find many of them online in any library. You can find pre-trained neural networks, get the embedding, the representation of the images, and compare them directly. Generally, this will give you a, let's say, fair enough performance that is in general working relatively well. But maybe if you have some, let's say, specific field of interest, like, let's say, face recognition, document retrieval, etc., maybe you want to fine-tune or train from scratch your model to get a performance that is more, let's say, adapted to your domain. And how can we do that? How can we train this model? There are many different ways in which we can train this model conceptually. The first one could simply take two images, say, are they similar or not, and classify that. So 0, 1, binary classification, that's it. But it's I've been seeing that there are better ways to do that, and many of them use something that is called the triplet loss, where we will have not two images or objects, but three of them. We will have an anchor that is a, let's say, reference image, then a positive that is a similar image that we want it to be close to our reference, and a negative that is dissimilar from the reference image, from the anchor. And we want to train the model in such a way that gradually the negative images will be far from the anchor, and the positive one will be close. So we can see that, we can imagine that as a, let's say, the learning procedure, or a part, a step of the training procedure, one, let's say, iteration of the training procedure. And we try to move the negative one farther apart and the positive one closer, In general, we want the positive one to be closer than the negative one. As we can see in this desired condition, we can see that the distance from the representation of the anchor and the representation of the positive should be smaller than the distance of the anchor from the negative by a margin alpha. So we're not satisfied by the fact that is smaller the distance between two similar images than two dissimilar images. We want that to be true by a margin alpha. Okay, so we are not really trying to make all the similar images go to the same representation. So we don't necessarily want this distance, the distance between the blue and the green dots, to be 0, because that will, let's say, be too restrictive. We will lose representation power because it's a very strict condition. And also, we don't want the distance between the anchor and the negative, between the blue and red, to go to infinity, because also that will be too restrictive. We want to have a, let's say, safety margin alpha between the two distances. In that way, the distance between the anchor and the positive could be also non-zero. And in that way, we can, let's say, maintain some, let's say, granularity in our definition of distance, of similarity, since we don't force all the similar images to be very, 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 very close. This should simply be closer than the dissimilar ones. In that way, maybe the learning procedure could preserve some spatial structure, for example, between white shoes. Maybe we'll have a pair of white shoes that will be more similar between them than other ones, since, again, we're not forcing them all to class in the same cluster very, very, very close. We are simply wanting them somewhat near and the similar one to be a bit farther apart by a margin alpha. Sorry. Okay. To do that, we cannot feed this condition directly inside the model, because the neural network cannot be trained directly by this inequality. But we will use the loss function, the triplet loss function. We can see here the formula. Maybe we can reason about that later if we have time, but in general, you can simply see that is what you obtain if you take this part of the equation, move them on the left, and so that we get a minus, and you take only the positive part of that equation, that is the square with the plus. So what we are trying to do is to say if that condition is not respected, so there is a violation in this condition, try to update the neural network in such a way that this violation become smaller till it becomes 0. Okay, so at the end, our network will try to converge in this case where we have the safety margin alpha, and we will have no cases, or let's say less and less cases of this condition where the negative one is closer than the positive one. Okay. Again, I did put a reference of the original paper, FaceNet, that defined this kind of loss, and it's a few years back, 2015, but it seems a century ago from let's say artificial intelligence point of view. Now we're almost at the end of the initial presentation. I present you briefly the data that we will be using, but you can use any data that you want. We have 3 classes of documents: driving licenses, social security card, and a generic other definition of document like the recipes, etc. We also have photos, scan, and generated images to also have some, let's say, variety in the dataset, and images of different sizes. This dataset is small since we don't want to spend too much time on, let's say, waiting for the training procedure to end. And let's say we want just to get an idea of things to work. We have 600 images in the training set and 150 in the test set. And so I think that now we can move to, let's say, the coding part. So I can close here. And I have prepared a virtual environment for today, okay, where I have installed a few packages. So I can show you the important ones. We will be using Keras to train this model today. I have installed here TensorFlow 2.9 since I'm using Windows today, and the latest version does not support Windows. The latest version TensorFlow does not support Windows. I also added TensorFlow add-ons since this package does contain the definition of, let's say, the implementation of the triplet DOS, so it will be a bit faster to use. Sadly, since I recorded material for the course for Project Pro about Siamese neural network, TensorFlow add-ons have been deprecated, so it will be supported. The maintenance of this package will be supported only till the next year. And so probably in future, you could use some other implementation of the triplet DOS. You could try to implement it yourself or find some other package that does it. But if we have time, maybe we could also try to implement it by hand if we have some time at let's say after the coding section. And then I installed also the common packages NumPy and matplotlib, where it is. Okay, matplotlib and Jupyter Notebook, Jupyter Lab, all the stuff to use Jupyter. So I don't know, if you want, you can try to see if you have these packages, or if you want to use some other packages. Okay, if you want to use PyTorch, JAX, the idea are the same. Simply, I will be using Keras for that one. I don't know if you want to have a couple of minutes to install the packages, see if you have everything. If you want to try to code now, maybe we can do a 2 minutes break, and so that everyone is a couple of minutes to, let's say, install everything and see if it can work. In the while, I can maybe try to open Jupyter. And maybe if it's okay, we can make 2 minutes break and see you back with everything installed. And so you can see there is someone with some question also. Okay, I can maybe see if there are some questions. Okay, this is more general. Okay, I see some question. Why is it called triplet function? It's a triplet because we are using 3 elements to define it. This other question is about the value of alpha. If we can use smaller value, could make convergence faster, but more sensitive to noisy data. We can use a hyperparameter to find the best value of alpha. Clearly, yes, we can use any other, let's say, any technique for, let's say, training any kind of model to see which value is best. Consider that training neural networks at scale is not really fast, so you will not be able to test too many values. Generally is, let's say, something not too big, not too small, something like maybe 0.1, generally okay. Consider also that the embedding will be trained according to your, let's say, will be trained in such a way that the alpha is respected. So if you start with a pre-trained model, maybe you can try to see how big is the, let's say, the range of values in your embedding to find some reasonable value of alpha. Maybe you could try also to, let's say, use a grid search before the training if you use a pre-trained model. So you compute embedding for all the values and see how the value of the triplet loss changes at varying alpha, and you can, let's say, see if you find some reasonable value. Okay, again, about the name triplet because we use 3 elements. Colab, we will use Jupyter Lab, but if you want to use Colab, it's okay. Okay, maybe we can packages list. Yeah, but there are many of them. You simply need TensorFlow, TensorFlow add-ons, or to implement it, implement by yourself the triplet loss, NumPy at Matplotlib. So only TensorFlow and TensorFlow add-ons, really. Okay, sending the codes file in the mail. I don't know, it's possible. Shraddha is have been the dataset shared with people.
Sorry, sir, didn't get your medium.
If someone is asking about the dataset, I don't know if it's possible to share it in some way with the people following.
How, what is the file size of the data set? Can we maybe upload it on Drive and I can share, you can send me the files, I can upload it on Drive and provided.
Okay. Okay, increasing the font size, yeah. Hope this is okay. Okay, is there the drive somewhere? Maybe I can show to people how to get the data if they want. Maybe I can show you also how the data is formatted for a moment. We have this folder dataset with 2 subfolders, one for training and one for testing. Then the 3 folders, one for each class of our data, and all the images inside. You could also have some other format. You could have, let's say, all the images in the same place and maybe some text file containing the class and training validation set inside it. Or you could have some, let's say, binary format like TF record, etc. But let's say the idea is the same. Simply you need some different way to load it. Okay.
Can you send me the file? I'll maybe.
The file, okay. I can send you by mail. I don't know how big it is.
Okay. Or Amedeo, is the entire data set necessary? I mean, you can just include a few images, right? Or do you have to include all images?
Okay, yeah, we can also use a few images.
Yeah.
We could, let's say, maybe we can try to do the same with a public dataset so that we don't have this issue.
Okay.
It should be, let's say, possible to do the same. We can use simply something like a Minist also. We can try with something like that, so everybody will have no issue with the dataset.
Okay.
Okay, now we can start. I simply start with the empty notebook. If you want to use Colab, something else, it's the same. Your choice. I simply import the main packages. So we import OS, NumPy, and matplotlib so that we can plot mat. Okay. Oh, mat. Okay. We have these packages. I will also load now TensorFlow, and from TensorFlow Keras. Okay. Generally, when I import TensorFlow, I will also plot the version to screen to see, okay, since there is always some compatibility issue depending on the CUDA version you have installed with other packages, etc. And also to make sure that I can get access to my GPU, I generally look into config list, if I remember, physical. Okay, that one. So that we can see the devices we have on this machine. Okay, we can see here I have a CPU and a GPU. Okay, my GPU is nothing too fancy. It's something quite old, but is useful also. Also, this old GPU is useful when working with images. Will make everything a bit faster. Then I also load TensorFlow add-ons as TFA. Okay. I will print also to screen the version of TensorFlow add-ons, since we need to be sure that the TensorFlow version and the TensorFlow add-ons version are compatible to make them work. You can see them in. Okay, here you can go and look for the compatibility. As you can see, as I said, there is it will be no it will be let's say deprecated since May 2024. There will be no, let's say, support after that period for, let's say, some reason, Google killing some other library. But for the moment we can use it, and maybe we'll try to implement our own version of the triplet loss if we have time. For the compatibility, you can see here that there is this table with the version of Python and TensorFlow you're using, and the version of TensorFlow add-ons you should be using to have compatibility. In my case, I have TensorFlow 2.9, and so I installed TensorFlow add-ons 19. And as you can see here. Okay, now we can start to try to load the dataset. Simply put, I will look how I can get the training dataset. So let's see, or we can also do like that. No, I'm not using, I'm on Windows. So, okay, I take the dataset. Oh, we say to use some other dataset. So my fault. So from directly from Keras, let's see the list of data sets we have here. So I do something like that. We could use the minced dataset or fashion minced, better, a bit more, let's say, slightly more complex data. Okay. Let's see. Model object is not okay. Load, something like that. No, load data. Okay. Okay, it's unloading the dataset. Maybe just while this is downloading the dataset, we can simply see how I could have loaded the data from my folders, if you want. This is in the original material from the course. You can see there is this utility function that is image dataset from directory, where you simply have to put the name of the main directory, the training data or the testing data directory, the image sites that you want to keep. So you have to define how the images will be resized, and then you can put the batch size, and if you want to shuffle your data set or not. Okay, you can put false if you don't want to shuffle the data set. You can put none and the data will not be batched, or you can put, let's say, a number 32, 64, etc. if you want to batch the data. I think maybe in the latest version of TensorFlow and Keras, these have been moved to utils from preprocessing. So maybe if you cannot find this function inside your installation, maybe you can go check if it's in Keras utils. But let's say we will get the same thing again now here. Okay, I've downloaded data. Maybe I can put the data. I think that is something like X train, Y train equal X valid, Y valid. Should be something like that. Okay, now we can go to look, let's say, the size of this data. Y train, shape, X valid, shape, Y valid, shape. Let's go to see. Okay, yeah, we have a bit more data, 60,000, 28 by 28, and 10,000 in the validation dataset. Okay, let's see maybe a couple of images from that dataset. I will start from the first one just to make sure that I can get everything right. So the first image should, okay, we can see it's something like a shoes. Maybe let's see if I can reshape it like that. No, expand. I want to reshape the X to have a final dimension, the channel. It would be a black and white image, not like that without the shape, because we will need, let's do like that. Shape plus, even better. I can do better than that. I want to add the final dimension of the channel because at the moment we have the say, number of images, the width, the height of the image, but we have not the number of channels. So I can expand the number dimension. -1, and the same for the validation data. X valid. Okay, now we have the channel dimension. We have just one value. Let's see if now it's in black and white. No, it's again the same. Maybe, I don't know if we repeat the same channel 3 times, if we get a black and white image, we can try. Instead of that, we can try to stack the image 3 times. Just experimenting about. Okay, now it's a black and white image. I don't know if there is some better way to convert these mono-channel images to black and white. Maybe if you have some other idea, you can share. We can go look. Okay, yes, I will share my LinkedIn profile at the end. Okay, now we have our images. This is just one. Maybe we want to plot more than one to look through them. So maybe I can plot a matrix of images. Maybe let's say 5 by 5. Okay, now for E in range 5 and for J in range 5, I will plot an image like that. IJ, I put the indexes, and so I will take the subplot numbered by I and J and plot the image in there. At the moment I keep that one, I will get, say, 5 by 5 of the same image. Okay, 5 by 5 of the same image. Now I can do something like I plus 5 times J. and I should get different images. Okay, yeah, we have a bunch of images and different kinds of them. We have shoes, we have t-shirt, we have trousers, etc. Okay, I could try to make this plot a bit nicer if I remove the ticks, etc. Maybe we can try. I don't remember by memory. I don't remember. Set x ticks. Something like that should be, I think, but I'm not sure if this doesn't work. We can go to check the old code. Okay, the same for the y-axis. Okay, a bit nicer. Okay, cool. We have this data, and now we could simply, let's say, take these images as they are in the NumPy array format, and Keras can work with them. Any library can work with them. But I want to show to you how to put the data from there into the TensorFlow dataset that is much, let's say, in general, faster and more flexible for many things. So now let's create a dataset. I need to do something like that. Df data dataset. And I have this utility function that should be from tensor slices, something like that, from tensor slices. Okay. And I will put x train and y train in here. Let's see how long it takes. Okay, done. Now I have this dataset, TensorFlow dataset object that has the where each element on this dataset is defined as a pair of objects. The first one is an image of size 28 by 28 with 3 channels, and the second one is let's say something without a shape, so a scalar number that is the class as an integer defining the class. Again, we can maybe go to look here. Is a good idea to have something like p max of y train to see how many classes we have. Maybe something like that. Print and classes. Okay, we have 9 classes. Cool. This is the dataset. And we will get the same. I can show maybe again to you in the whole code. In that way, we would also get a training dataset from the training data. But instead of loading it from the NumPy dataset that we got in this way, we will get it from the files in our folder. This is quite handy because anyone can work on the, let's say, images in the folder, move them around, create a new, let's say, class by simply defining a subfolder with a name, etc. So everybody can work with that. Also, if maybe there is one person that is writing the code and other people that is classifying images, etc., even if they are not expert in machine learning and AI, that is useful. And so let's say, keep in mind that this function exists, but again, we will get the same, let's say, kind of objects here in this way. Okay. I print here since we get these informations. Now, what we want to do with these objects? We want to apply a few transformations to it. The first thing we want to do to make it possible to work with it is to convert it to a to float instead of integers. This image is defined as small integers, so it will probably be numbers between 0 and 255. Generally, images are defined like that. So maybe we can go to look also to that. X-train mean and max should be between 0 and 255. general, something like that. Yeah, between 0 and 255. We want to, let's say, get the image defined as floats between, let's say, either there are a few possibilities, between -1 and 1, between 0 and 1, or following a normal distribution if we want to, let's say, change the distribution itself, but let's say I think it's not advisable in that case. I would probably simply divide it by 255 to get, let's say, images in the 0-1 range. So I can apply a transformation in this dataset. With the map function, I can put here any function, but in that case, I will define it by a lambda that takes to input the x and y of our dataset. Here we have the x and y. And the y will stay the same. We will not change it. While the x will be defined as x divided 255, like that. I can try to run to see if it works. Same, must have the same D type. Oh, something changed. Let's see how it did something like that. In the old code. Yeah, it was, no, here was already in the float. Why it's not working that? Maybe I should do tf cast x float 32. Okay, okay. I needed to cast it before dividing it. Okay, now we can try to see, let's say, look inside this dataset to see if we're getting something that we like. Generally, if I need to do something like that, I will simply try to get a batch of data, x and y. I call xb and yb because x batch and y batch. And I will take just one. I can see it. Okay, here I get a tensor, but I can convert it to a NumPy easily. Okay, we have our object and see now that is a float, not an integer. And we should be able to plot it like that again, just the first one. Not in show. Okay, maybe, oh, okay, we have one image just. Okay, we get again the first one, since we have not shuffled our dataset yet. So maybe I can do something like that so that we will not need to run everything again. Okay. You can see it's again the first one, since we have not shuffled it. So maybe here, then we can put some data augmentation, but for now, we will do it later. We can simply try to shuffle the data with a buffer of 1000, let's say. So we will take the first 1000 images, shuffle them, get one at random, and then add another one from the, let's say, the queue after it. And okay, now we get a different images, and every time you run it, we will get a different one since we are shuffling the dataset. Okay, cool. Now we, let's say, need to do another thing before we can feed this data to a neural network to train it. And this one. We need to fetch it, batch 32. Okay, let's say we start with something like that. It should be sufficiently small to run in our GPU, but we can maybe change it later if it's not working. Okay, now this will not work anymore. Okay, because now XB is a batch of images. Now we need to do something like that. Okay, so now maybe we can plot a couple of them. Maybe again, we can do again a matrix of plots. 1, 2. Let's say a bit more than 2, 4, for example. And let's say for in range 4, X E im show XB I. This is X. Let's see if it works. R. Oh, okay, not R, but 4. Okay. Okay, now we can see a few images at random. Okay, now we should do the same thing for the test, the validation dataset. Okay. Train dataset, valid dataset that is again from X valid and Y valid. In that case, I will not need to shuffle the data since I would simply need to, let's say, look into it. And also, test time, data augmentation is a bit complicated. So we will not try to do data augmentation on the test set. It's possible to do it, but you need to be more careful and a bit more conservative with that, because otherwise it would, let's say, get a wrong estimate of the performance of the model. Okay, but now we have our train and validation dataset. Now we could do two different things. We could try to define a neural network from 0 and to train it from scratch, or we could try to get a model from, say, a pre-trained model and fine-tune it. We would do that since it's much faster, and also in general we would get a better performance unless we have huge amount of data and we can train for longer periods of time. There should be some models here in Keras applications. Here we can look at all the data that all the models that we have. We could try maybe something like either EfficientNet or MobileNet. I think in the old one I use that one. Okay, in the, let's say, in the course, the regional course, I use that one since it's quite small and fast to use. But depending on the performance you want to have and on the, let's say, how big the machine that you are going to use is, how much time you have, you can use any model that you want. There are smaller and bigger ones. Now let's see if I can download it. Okay, it's loading it. It will just take a minute or so. Okay, now we can start to talk another important detail about the triplet loss. We said that we have each time we want to compute the triplet loss, we need to have three items, three objects, three images, one reference, one similar, and one dissimilar. But how can we define these similar? How can we not define, but find? Let's say in our case, in our application, we will say that two objects are similar if they are from the same class and dissimilar if they are from different classes. But how can we find the possible triplets? There are two main possible approaches. Let's say maybe we can write a bit of stuff here so that we have loss. We need to do something that is generally called triplet mining. So we need to find the triplets that we are going to use to train the model. There are two families of approaches that are offline triplet mining. That means that we will look for all the triplets that we will be using in one epoch. So find all the triplets that you will use in the next epoch. So I take all the data set, find all the triplets that you want to use. So I take one image, one similar, and one dissimilar, and I will train the model for one epoch and update it again and again and again and again. Then but they say that is time consuming because I need for each epoch to stop and look at all the data and make a selection, etc. So it's generally not the preferred approach, but oftentimes online triplet mining or also batch triplet mining where we look for dissimilar and dissimilar items inside one batch of data, in our case, 32 images. We look for the triplets inside one batch of data at a time. Now, there are also in this, let's say, in the online triplet mining case, there are a couple, a bit more than a couple, a few ways to do that. The first one, that is the simplest one, is all triplet. So I take all the possible triplets of anchor, positive, negative inside the batch. So all of them. I put no restraint, no constraint, nothing at all. All of them. Then there is the hard triplet case where I want to take only the hard negative. So the negatives that are farther apart than the margin, so the difference is greater than the margin alpha. And these are the hardest cases for the model to classify. So we want, if we use that approach, we want to be aggressive with the model, force it to train on the hardest triplets first. And this is advantages and disadvantages. It depends on the case. In general, it could be too hard for the model, and it can force it to learn too fast. And the other approach is the soft, the semi-hard, sorry, the semi-hard triplet, where difference is lesser than the margin alpha, but the negative is still closer than the O. I can maybe take the slide again for a moment so that we can understand a bit better with the formula what this means. Again, I say that we want the positive to be closer than the negative. The hard and semi-hard cases are all the cases where the negative is closer than the positive. So all the cases where this condition is not respected. Oh, no, sorry. The hard negative are the cases where this is true. The semi-hard are the cases where it's not. Sorry, I need to correct that difference. The negative are that one. The negative is closer than the positive. The semi-hard are the cases where the positive is closer than the negative, but less than the margin. Okay, so the hard cases are the cases like that one, where the negative is closer than the positive. The semi-hard are the cases where the negative is farther apart than the positive, but the difference is too small because it's smaller than alpha. And so we still have to, let's say, make it farther apart. Then there are the easy cases where the negative is farther apart than the positive, and the difference is greater than alpha, so the loss is 0, and the model will learn nothing from it. Okay, so the easy cases are useless for the model, are not useful for training the model. So we need to focus on either the hard or the semi-hard ones. Okay. So, okay, we see that in TensorFlow DOMS we have both of these cases, and it will do everything for us. If we want to implement it from scratch, this is the easiest one to implement. But again, also this one are possible to do. Okay, now we have downloaded the model. Maybe you can move that above. Okay, now we need to define our, let's say, complexity model. We'll do with a sequential model. where we start with the CNN, the convolutional model, where we don't want to include the top. Oh, just, I don't know if this model is capable of handling the 28 by 28 images. We will see. Let's see. Include top, false. We don't want to include the top of the model, so we get okay. Okay. Now we get all the embedding, but this is a still the, let's say, the image dimension. We want to remove it, so we can compute the average using a, for example, global average pooling layer. In that way, you see that we have the width and date of the image yet. Now, okay, in the output, we don't have this dimension anymore because we have computed the average across these two. Okay, let's see. The smallest possible dimension for the images here is 96, so it's a bit too big for our case. I don't know if we have some pre-trained model for images that small, 28 by 28, like in our case. We could either try to, let's say, upsample these images, but we will lose, let's say, much of the information, or maybe we can try to, let's say, train it from scratch. Maybe after that, we can try again with the pre-trained model using, let's say, the other dataset. But if we want to use the this, let's say, small dataset of smaller images, this model is too big. It cannot handle well these images that are small. Let's see if it can run, but probably could be could have some issue. Let's say here, this is a, let's say, optional part at the end of the model. We could use something that is called normalization, like that. I put the lambda, keras, not layers. What is this called? Let's see. We can try to normalize the embedding at the end of the model to make sure that we will not try to, let's say, collapse to zero. Will not try to go too close to the origin to make everything the same. Okay, like that. They can help to normalize. Okay, in that way, if we use that function, we'll make sure that the norm of each embedding is 1, so it'll be living inside on the surface of a n-dimensional sphere. So the representation of the images can move across this sphere, but it will not go inside, so will not try to collapse to just one point. Let's see if, well, let's say in theory, if this model is the pre-trained model can handle images that small, we should be almost ready to train our model. We should be able to do something like model.compile. We define the loss, that is TFA.losses. And we can see that we have the triplet losses here, the hard, where we say the negative are closer than the positive, and the semi-hard, where the positive are closer than the negative, but we are not respecting the margin alpha that we want. We can try with that maybe, since it's generally a bit more stable. We can define the parameter alpha, like 0.1. Maybe, I don't know, the default. Let's see what the default is. Let's see here in the documentation is 1. Oh, margin, not alpha here. Okay. The margin is 1 here. So maybe let's start with this value. Okay. Then if we want, we can add some matrix, etc., but we need to find before the optimizer. we can use, let's say, the classic Adam here. I will start with see, constant learning rate. But if you have experience with the training neural network, you know that oftentimes it's better to use a schedule. So there are many different schedules, but the general idea is to use different step size to update the model, depending on where we are in the training time. So generally, the idea is to start with a small update so that the model can somewhat warm up, increase the step size so that the model can update faster in the second phase, and then again reduce the learning rate so that we don't have too much risk to, let's say, decrease the performance of the model due to overfitting or something like that. But for the moment, let's start with that. Okay, we could also add some metrics if we want, but let's say it's not necessarily the case. We will be looking for the loss. Okay, now in theory, we should be able to simply use the train data set and the validation data set like that, defining number of epochs, let's say 10, just to start. And the batch size is not necessary since we defined the batch size in here. But I don't know if this will work since, again, the issue is the model size compared to the size of the images. Let's see. Validation data is valid data, maybe valid data set. No, what's the name? Valid. I did not define it, maybe. Okay. Let's see. No, it's complaining. Let's see why. Yeah, you can see here that the issue with the size of the images is presenting itself. You can see negative dimension size caused by subtracting 3 from 2, blah, blah, blah. The dimension of the original images is simply too small for this model. So let's say we could either use the other data set, but I want everybody to be able to work on the same stuff. We could upsample the images, but I don't really like that because we get, let's say, images with squared groups of pixels and weird stuff. We could try to, let's say, train a very, very, very small model with convolutional layers from scratch. Maybe just one couple of convolutional layers. Okay, we simply need to define the number of channels in the output and the dimension of the convolutional kernel. Let's say maybe 5. Okay, just simply like that, maybe a couple of layers, and the padding also. Let's say no. Let's do something very simple. I don't want to spend time trying different architecture here. I simply put a couple of convolutional layers. I didn't want to spend much time about that. In any real case that is not on a toy, let's say a toy dataset, you can use a pre-trained model and it will get, let's say, get better performance from the start. Any model inside the Keras application or any other, let's say, pre-trained model will work fine. Let's see. Now the model is not okay, it's not built yet, so we cannot show the model summary, but we can build it. This is not necessary simply to show the summary of the model, number of parameters. We need to say that the shape of the data set would be 28, 28, 3. Okay, now our model is very, 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 very small. We have only a bit more than 10,000 parameters. And let's see if it can run. Let's say if it can run, we have some, oh yes, we have something that is, let's say, going. It will take not too much time, but maybe I think if we can make it go a bit faster if we increase the batch size, since this data is very small, much smaller than let's say, the other data set. So maybe we can try like that. Let's run all and see if it works. Okay, if this works, we are in, let's say, a first checkpoint, let's say, for our data set. Okay, you see going a bit faster since the batch size is much larger. And also this is, let's say, this model, for this model is important, batch size, since, as I said, the triplet loss will go to, let's say, look for the triplets inside each batch. So it's important to have a batch size that is big enough to find some reasonable example. So maybe while this is running, let's look for a moment if there is some question. Yes, the code will be shared. The recording, I don't know about the recording, but also I think yes. Yes, the margin and alpha are the same thing. Simply this implementation call it margin, but it's the same thing. Okay. Now, I don't really know what will happen with this training, since we're starting from scratch with, let's say, random convolutional neural network in here. Probably this is far from optimal. We should go to look how to define a very small neural network, the right combination of filters, strides, pathing, and everything. But let's say this probably should some more or less work. Okay, you can see that the loss is somewhat decreasing for both the training and validation datasets. Probably 10 epochs is too small for training from scratch. We probably need many more iteration. We will also need to define a better schedule. But let's say we get a first idea, we can go to look, and then we can try to improve things a little bit. Maybe we can try to add some data augmentation and stuff like that. Okay, again, probably will not move too much in a couple of iterations. Just let's wait a minute. Okay, just a bit lower. To train from scratch, probably we will need at least 10 times more iteration, or also somewhat bigger model, etc. But I don't want to spend too much time optimizing the performance of the convolutional neural network. Because let's say, let's be realistic, in 99.9% of the cases, we will start with something like that, or also, let's say, some other model. This just was the smallest one that is quite small, but you can start from any pre-trained model and use it like simply, let's say, removing these two lines and using that. Let's add a comment also from pre-trained model, or here from scratch. No, scratch. Okay, and here, yes, put the embedding to 1D vector and normalize. Okay, a couple of comments, so maybe it's useful if something of you want to try it. Then here is the size of our images. That is not strictly necessary, but it's useful to just look in the summary and see, okay, this, let's call it mini training, is finished. Maybe we can go to plot the loss function, the history, the loss during the training. Loss and, well, oh, something wrong here. Okay, history. Should be like that. Okay. And this is val loss. Let's put, I don't know which is your favorite color. Let's put a blue for the training and a red for the validation. Let's see. Okay, you can see both of them reduce a bit, not too much. Probably we will need a somewhat bigger model, better designed, and to train for much longer. But let's say this get a first idea. Y scale log. Okay. Okay, you can see it's decreasing. Maybe later we can try to train it for a bit longer. Now, we want to see if, let's say, we're getting some meaningful definition of distance now from let's say, from this model, and how we can use this, let's say, model to find for similar and dissimilar images. So what I will do now is simply to take the model and predict on the images x valid. They should be divided by that. Or maybe also I can also do something like that. Valid dataset should work. Yeah, okay. Or not. Why is all 0? Let's see. Let's call it red valid. Okay. Okay, let's see. The shape 32 should be right. Okay, we have 32, so it's right. But let's see that the sum is not 0 because it, okay, it's not 0. Okay. Okay. There are some, let's say, some features that are always 0, but this is not an issue. The important thing is that we don't have everything at 0 all the time. Let's see to get an idea on how the things are distributed inside it. Okay, too big. Let's see the first 100, let's say. Okay, you can see each the representation of each image is along a 32 long vector, and we are considering the first 100 images. You can see that there is some pattern in there. I wouldn't, let's say, look into too much significance into that, since, as again, this is just a model trained for 10 epochs on a smallish toy data set and with a very small neural network. So simply a bit more than random noise, but we can see there is some pattern. If our model is trained correctly, we should have that images with similar patterns have similar, let's say, meaning for us humans. Now, we can use these, let's say, you can do that, the predict, also useful to know, simply with x valid, dividing by, let's say, making sure that the range of values is the same. So this should, okay, go. Now, we can take an image, let's say, we can take the image 0, and we want to go to look into all the others and search for the image that is the most similar to the first one, okay? So we have this red valid I, okay. Okay, this vector with all 0, but just these two numbers is incredibly sparse to be, let's say, trained without this into mind. But we want to look for all the others dataset and search for the images that are the most similar. How we can do that? Okay, this is, look, a red valid shape. Okay, we have a 32 vector and then a two-dimensional vector, this 1000 by 32. This is not too complex. What we can do is to look at the square difference, the Euclidean distance. We want to red valid I, and to remove element-wise this one. Clearly, we can do that directly because this has one dimension, this has two dimension. What we can do is to reshape this one in that way, 1 minus 1, so 132. In that way, we can subtract this, the representation of the first image to all the other ones. Okay, and then we can square it. So we get the square distance for each element, and we simply compute the sum across the vectors. You can see now we get a vector of shape 10,000. That is the number of images we have. That represent the square distance. To get the Euclidean distance, we would need to take the square root, but this is not necessary to compute to find the ones with the smallest and greatest distance. You can see that there is one element that has 0. That is clearly the same, the first, since the distance of one object from itself is let's say 0 by definition. Okay, we now should look for all let's say the second and third, etc. distances in that vector. So we can call that D2, that is the square distance. Compute the square distance. Okay, and now we can take the arc sort like that to go into looking to the, let's say, to the closer and farthest apart elements. Let's say this can be, let's say, a slow function if your vector is very, very big, because it's a, let's say, sorting algorithm. So we'll have a complexity of O and log n. But let's say in the case of 10,000 is not too much. If we want to be faster and we want simply to go into looking into, let's say, finding the most similar item, we can simply do something, the arc mean of D2. We cannot do like that because clearly we get 0 again. We need to exclude the 0. So maybe do something like that, or many other way, since some masking here. You can see you get again 825. Or we can implement let's say, loop that is let's call it a partial arc sort that takes only the first one. I don't know, maybe we can go into looking if NumPy implements that. Let's see the documentation for the arc sort. Okay, here you can select the algorithm, order. Okay, no, we don't care about fields, it's simply a number. Okay, we could simply say, do something like that. You want to find only the first elements, or maybe something like masking. We can also do something like that, and P where D2 equal 0, we can put infinity, and otherwise we can put D2. You should get 26. Okay, because before we were, if we take that one, 26, and again, we have the same. In that way, we are simply saying that when the distance is exactly 0, we want to put infinity instead, so that the element itself is ignored, and any other duplicate is ignored. Because if we have images that are exactly the same, we could also find them in this way. So let's say this is also interesting, is another possible application, looking inside the dataset if there is some duplicate image. Okay, some duplicate image, some duplicate, let's say, observation. And this is often a problem with datasets that are very big, because you cannot go into looking by hand if there are equal images. And it's a problem, especially if you have one copy in the training and one copy in the validation. In that case, you get, let's say, a wrong estimation of the performance of the model. But it's also a problem if you have it in the same set, because you get, let's say it's not optimal. But again, now this 10,000 is not too big, so we can take all the list. We can put the indexes by similar. Okay, now we can go into something like that. We want to plot all. What's first thing? First thing first. Let's see how the distance is distributed. Plot east D2. Let's see. Okay, beautiful. You can see, maybe let's add a bit more definition. Okay. Okay, you can see that the distance is between 0 and 2. This is because we forced the, let's say, representation of the item to be on the sphere by normalization. Again, you remember here we did put where is it? Okay, here we did normalize the representation so that the let's say the norm of the representation is not too big, so it's always on this multidimensional sphere around the 0. If we didn't put that, we could have any value, could be much smaller, bigger, etc. But let's say these seem to be good. We have a spike here of that is not too big. That is something like a few thousand elements that are probably the items in the same class. And you can see here that there is a pile of elements that are quite dissimilar. And then there is something in between that items that are a bit in the between. Okay, now we can see maybe one way to understand if the performance is good could be to do something like that. We can look if the valid, when the y valid is y valid I. So this is the distribution of the items that are in the same class, maybe color equal 3. And we can do the same for items that are in a different class. Yes, it's probably covering. Oh, green and green, no, red. Okay, you can see that the majority of items that are in the same class are very similar, but with some, let's say, differentiation, while the majority of items that are in a different class are quite far, but there is some, let's say, small overlap here of, let's say, errors of the model or items that are somewhat similar aesthetically or maybe something like that, but we can go to look into that. Again, now we have the indexes by similarity. We can do something like that. Fig arcs again, these subplots. Let's start with maybe 5. And then for j in range 5, I will show on the j plot in show x valid, the image x valid of the index by similarity j. Okay, so I will show the first 5 elements in this list in the most similar items. Clearly, the first one will be the item itself. Okay, we have distance 0, so the item itself, so we can see how similar it is to the other 4. So we have the item itself and then 4 other items that are the most similar. Okay, you can see the reference image in that case is show, and we have 4 others. We can repeat, we can do that again for other images, for many of them maybe. We can do maybe repeat the same for, let's say, 10 times, something like that. We can, with the distance is computed just once. We don't need to compute, no. Okay, we didn't compute the matrix of all the distances. We did compute the distance only for that item. Okay, okay, we can go like that for E in range 10. Okay. Okay. Okay, we can start like that. Let's see if this works. Will take a few seconds. Okay. You can see these are the items, the images that we chose as a reference. And here you can see the most similar items. Okay. The 4 most similar in all the validation data set. Again, remember that the model didn't see any of these models in the, let's say, in the training. So it's simply, let's say, looking by, let's say, we're looking at the real performance of this model on this, let's say, kind of data. Clearly, if we put some different images, for example, images that don't have the black background, have colors, something like that, maybe it could be a bit different. But let's say you get an idea. You would need the real world images to make it work on real world images. So you need the same kind of data for the training as for the validation. Okay, now I would also like to add other 4 images that are the 4 that are the most dissimilar. So instead of 5, I will put 1 plus 4 plus 4. So we can remember that is 4, the original item, the 4 most similar, and the 4 most dissimilar. To do that, I will simply need to repeat something like that. For j, again, in range this time 4. No, let's say 1, 5. And we'll put minus j, and this will be 5 plus j, I think. No, 4 plus j. Okay, should be like that. So since here we are looking from the, let's say, from the tail of the list, we are looking at the items that are the farthest apart from the original image. So let's see, let's go to see what we get. Okay. You can see maybe let's say, because I like it better without all these let's say all this stuff. Okay, should be a bit better. Oh no, it didn't work. Why? Oh, because I need to put inside of them. Sorry, but I need it to be a bit clearer to reason about it. Okay. Let's see. Okay. Now remember, in the first column we have the reference image that let's say the item that we gave to the algorithm. Then the first 4 are the most similar items. You can see that are all somewhat similar in all the cases. Clear. I'm, let's say, quite impressed that this small model on this very short training do somewhat work. No. And then we have 4 dissimilar images, and you can see that they all are different items from a different category, etc. There are some patterns. We can see that, for example, shoes are very different from trousers, but also some t-shirt there. Let's say this is not clearly a rule, and very dissimilar items are not necessarily, let's say, some meaningful thing, because the model could put them in many ways. Remember, the model only care about the margin. It don't care about how to put, let's say, dissimilar items at an infinite distance, but it does care to put them somewhat distant. So at a distance of at least 1, you can go to look there. The model will have no instant type to put the item farthest apart than 1, that is the margin. And the items that are pushed farther apart are simply as a, let's say, side effect of the training. It's not the direct effect of the loss that want to push them farthest apart than 1. Is that simply, let's say, it's easier for the model to do it like that, to push them farther apart. And let's say, because they want to be far apart from all the similar. So we'll get like that as a side effect. But again, we did not force the model to do that. So let's say I'm quite satisfied with that result. Maybe what our is, okay, maybe we have another few minutes to look into the, let's say, in some details of for all of that. Okay, we can go to maybe implement some data augmentation for the model. Okay, we can put the data augmentation in 2 places, depending on our preference. We can go to put it inside the definition of the training dataset, or we can go put it inside the model itself. we can try to see both of the ways, so that maybe, okay. Another thing about the dataset that we can improve is to add after the batch function a prefetch that is simply telling to TensorFlow that you want it to, let's say, start to prepare the next batch of data before the model finish to train in the current one. So you will have the, let's say, model in the GPU running and training, while the CPU is trying to process the dataset as fast as possible to make sure that the model is running as much time as possible as a percentage. You don't want the model to stay idle to wait for the next batch of data because, let's say, the dataset pipeline didn't prepare it yet. You want it to be, let's say, always ready. You want to have data always ready to feed it to the model so that your training is faster than the possible. So here you need to say how many batch of data you want it to have always ready, or at least to try to have ready. But you can also simply to tell it, hey, I don't mind, define it yourself, auto-tune, find it yourself the optimal value, the best value that you can find. Okay, so we will try to do as little as possible to make sure that the model is always running. Okay, now we need to decide how to do the data augmentation of our images. Since these are garments, I don't want to put them upside down because otherwise we get something strange. But we can do something like that, maybe, just to start to get a feeling of what we would be doing. We can do TF image. Here we have some predefined data augmentation. And we can look into random, and all of that will, let's say, do some changes to the image. For example, random flip rep right. It will randomly flip half of the images horizontally. Okay, we then can go into looking at that, and then again, I always want to keep my Y. We can add something else, maybe also. For example, random brightness. I think we need to define how much we want to change. Let's say I did define all the data augmentation pipeline in the code file, in the, let's say, the project, in the file for the course from Project Pro. You can see here, there. Let's say, let's take all of this and let's maybe discuss how this works. Said here, we need to take also the parameters that I define. Where they're here, data augmentation partners. Okay. Okay, we are changing. We're flipping the image left and right like that. We could also flip it upside down, but it's not always, let's say, a natural transformation from our data for our data. Then we can change the brightness of the image. We can define how much we want to do that. We can try to tune it a bit. Then the contrast, the hue, and the separation of the image, again, defining how much we want to change them. I define these values. You will see here the values just by trial and error, a bit of experience. Also looking into the default values in the documentation, and then try to, let's say, test it a bit and using my, let's say, best guess to find something reasonable. Generally, we can be quite aggressive in the training dataset to, let's say, try to give the model a variety of examples. In the validation dataset, as I said before, generally you need to be more careful about using augmentation. And generally, either you don't use any kind of augmentation to get the performance analysis of your model, or you can do it, but generally it's recommended to give many repetition of the same image to the model and average the prediction. So for example, if I randomly flip the image left and right, I can give both of the possibilities to the model and then average the prediction between the two. So that generally this can marginally increase the performance of the model, So for example, I could do for the validation dataset the same augmentation pipeline, maybe with values that are a bit more conservative, so changing a bit less the images. Repeat the prediction process 10 times, or 5 times, 10 times, 20 times, as many as you want, and average the prediction to improve a bit the performance. But this is not necessary, and I don't want to spend too much time on it now. Let's simply go to look inside how these influence our images. See, you can see that we have this image that where the background is not black anymore, is a bit different. Maybe I want to give you more examples. So maybe let's put 10 and let's do, yeah, let's do something like that. For 10 and 10 ij I plus 10j. Okay, again, let's remove the ticks from our plot so that is a bit nicer. And maybe I did maybe also something else to make the plot nicer in the code for the course. Let's see, so that we get some nice plot. Show. Okay, I did remove them completely instead. So let's do that so that we get some nicer nicer plot. And okay, that's it. This should be enough. Let's see. Okay, it's complaining that the range is not 0, 1 anymore. Okay, okay, maybe. Oh, okay. Yeah, right. Probably we want to do that after the data augmentation. Let's see if that's the case, because it works better with, let's say, the images in the original format. And after that, we can, let's say, try to convert them. In fact, it's not complaining anymore. Let's see if it works. What's the, oh, I. This should be a J. Okay, let's see. But it's not complaining anymore. So, okay, you can see that there is much more variety. Some of the shoes are in the other side, etc. So we have more, let's say, variety in our training data set, and we can, let's say, probably get better performance. But again, we need to train the model a bit longer to see that, and also we probably need a bigger model. The other thing we could do to do the data augmentation could be to use some keras layers. Preprocessing should be like experimental in that version of TensorFlow is inside experimental preprocessing. And we have, for example, all these layers. For example, since we didn't use the random, let's say, random rotation, we could use here. Let's see if we can find the documentation to see if we need to define some the parameters of this transformation. You can see in the latest version of TensorFlow, this is no more in the experimental preprocessing, but just inside layers. But since I'm using an older version, I need to go inside the experimental. And the factor of the rotation. Okay, the factor of the rotation. Let's see what it is. A float represents a fraction of 2 pi. Okay, how much do we want to rotate the image? Let's say fraction of 2 pi, 10% of 2 pi. Okay, 10% of full rotation as maximum. This layer is, let's say, quite smart in how it's working. It will do this transformation on all the images before everything else, since it's at the start of the model. And it will do it only on the training, okay? So it will not rotate images for the validation dataset unless we specifically say, hey, I want you to consider this like training. But in general, we'll do data augmentation during the training, and we'll do nothing during the, let's say, prediction. So in our case, this will change the training here, the fit, but will not change, let's say, it will clearly change the results of the training, but will not rotate the images during, during the prediction phase. If we want to do it, we will need to do something like model, valid, dataset, training equal true. Okay, if we want to see the results, but let's say generally we don't care. Okay, we can try to run the model again with this transformation. Again, remember we have done all of that inside the train pipeline, and we have implemented added the rotation here since it's already implemented in the layer. But we could do everything in one side, everything in the other. There is no, let's say, wrong and right way to do it. Simply, I find it easy to put it inside the model, so I don't need the data. But let's say about your preference on how to do things. Let's try to run all the code again to see if it works right. And maybe let's see also if it change the performance of the model. So let's see one moment the chat if there is some question. Okay, no new question. Cool. Okay, we look at all the data with the data augmentation. Here you can see again our model. Okay, and it's training. Okay, now let's wait a moment of two for the training to end. Again, there are many things. Again, we could try to do differently. We could try to remove the normalization if we want to let the model free to define, let's say, how to put the representations of the images in the space, in the, say, embedding space. We could try the triplet hard loss instead of the semi-hard. We could try different model, different stuff like that. We could try to implement the triplet loss ourselves, and maybe we can try to do that. Let's say there are many things, many other things we could do. These are the first things that comes to my mind. Let's see just one moment if we can do something. Okay, it seems that everything is working. See. The original code, I don't know about the original code since it's inside the, let's say, it's the course material, but there is more or less the same stuff, maybe a bit more polished. But again, I don't really know about that. Yeah, of course, but you can, again, someone is asking if we can run the same code with its own data set. Of course, you can. Maybe I can add the comment here in the start how you can load your dataset from, let's say, a folder with images. Here I can put maybe comment the let's say here load a standard dataset from Keras, and here load your datasets from local folders. Could be Keras processing. No, it's not working. It should be something like image dataset from folders. And maybe we can try either what's the dataset training data. Okay, there's some other question. Okay. Now let's see the training. Okay, we can see that compared to before, the model is taking much longer to train. You can see that before we had 0.7 as the, let's say, loss value. But at the same time, before was a little, let's say, moving up and down. Sometimes let's say, the loss was higher than the previous iteration, etc. While now it seems that it's smoothly moving down very slowly. That's let's say, common. It could happen often if you add data augmentation to your training procedure, since it will be harder for the model to find, say, the ways to adapt to the data. But in general, we will get you to better performance. You need to find the right amount of data augmentation, because if you augment the data too much, the model will not be able to train anymore. And you will get something like a flat curve where you get only, let's say, you're training on noise, basically, if you add too much randomization into your data augmentation procedure. If you do too little data augmentation, you will, let's say, go down first rapidly, and then you have the validation loss go up again because you will overfit on your data. If you find the right amount, you will be a bit slower in the training than without data augmentation, but you will get less overfitting, and so an overall better performance. Let's say you need to find the right amount of data augmentation, and also the right kind of data augmentation, depending also on your model, your data set, the say computational budget that you have, how much time you want to train on it, etc. You need simply to, let's say, to try to see which kind of data augmentation works best. Okay, you can see that before it was a little more, say, up now it's quite smoothly going down. But again, let's see how, let's say, this compared to the previous time. Right? Okay, again, we see some regularity, some values that are always zero, but I think it's due to the, let's say, normalization. And let's see here. Okay, again, with the first image, we get all the shoes. Now, let's try, we cannot see it very well, so we can try line, style, step. In that way, it should be, let's say, transparent, and we can see, oh, east type, like that. Okay, now you can see that something is, let's say, there is some regularity in that, since, again, the similar images are somewhat closer to the dissimilar ones, but the training is not complete yet. You can see there is this big bunch of stuff here, that there is some similar images that are quite far. Let's say the training is not ready yet in that case. But let's see the results just here to get an idea what the model is thinking. Okay, but as you can see that it's still working somewhat fine in that case. The most similar images are still very similar, at least by eye, I would say. I don't know what you think, but it is working fine, probably because if we go really, really, really close here in this small angle in the left, we have similar images, but probably we would get something strange happening if we go a bit farther apart. For example, if we go here, like here, probably, so if we go, maybe the first 10 images are really, really similar, but if we go a bit farther apart, it's less clearly defined. But again, it depends on the use you want to do on your with this model. If you're only interested in the most similar image, this is working well. Look, the first image is very similar. Again, here we have a very, very similar shoe. Here we have, let's say, a very similar jumper with, again, some symbol on top of it. Again, white trousers, very similar again. I think it's working fine if you only care about the most similar. But again, here you can see here and here there is something, let's say, In the middle ground, there is something that is still not working too well in this iteration, again, because the training would take more time since we have more documentation. Now, let's return for a moment on the data loading part. Okay, it should be, I remember, okay, image data from directory. Then, since I have the data, I can show it to you how it will give us the data. Again, you can see that it's very similar to the format that we get with this original line. Okay. It will give bigger images because the default, I think, is that, but it can image size. You can say that we want, hey, maybe I want smaller images because I want a smaller model, or I want really big images because I have big images and a big GPU and I want to try out a big model. But let's say I want to do something like that, somewhere in between. Then I don't want to shuffle data because I will shuffle it myself, or maybe it's the validation data set, so I don't want to shuffle. And you can see also, it's saying to us that we have 600 images belonging to 3 classes, and shuffle through. And let's say, what was the other thing? Batch size. If I want to define the batch size, I can. It will get batched. If I don't want, I can none. It will not batch data. You can see here is not batched anymore. But again, you can do this if you want. Train data set. Okay. Shuffle through here, and I can do the same stuff with the validation. It's calling testing data. Here I don't want to shuffle false batch. Maybe I'm okay with batching the validation data set. Okay, but let's say this is up to you. You can do again what you want. Then you still have to, let's say, do the documentation, batch data for the training, etc. Let's see how maybe if you want to add the data to this data set, how you can do that. You can simply, you can see here now we have 600 images from 3 classes. Okay. Now I go into the data set, the training data. Maybe I want to add a new class, and maybe is smile. Simple, no, smile. I can open Paint. And maybe simply do something like that. Can do something like that, save it to that one. Let's see where is data set, training data, smile. Clearly, probably you will not do it by Paint, but you have maybe some source from your data. Okay, here is our image, and now I should say that it has 4 classes. You see, 601 and 4 classes. So this would, you can, let's say it's very easy. If you have let's say a team of people working or something like that, it's trivial to make them understand how to contribute to creating this data set and classify the data. You don't need anything complex. But let's say clearly this will not be the most efficient way to do it from the computational point of view. So maybe if you want to do something big, after you have your data set in that format, you should look into how to save it into a TIFF record so the training will be fast. But let's say to experiment about it, train some medium-sized model with not too much data. This is, let's say, very good also for, let's say, making sure everybody can contribute. You have data in a nice format, etc. But again, now let's see again if there is some question we can answer now. Okay, the question is, how effective is Siamese neural network in supervised image classification against the normal methods as well? Is change those function? Okay, so how does this compare to classification? Let's say if our objective is only to classify the images, clearly using the classical classification method. Sorry for the, let's say, is better, is more specific. But we have not, let's say, guarantee on how the data is, let's say, distributed inside the classes. So we'll get only art classification. So if you only care about, maybe you know that you have 3 classes for your images, you will only always have 3 classes, and you will never add new ones. You don't care about, let's say, smooth transition between one class and the other, but only it either A, B, or C. Clearly, user classification algorithm is better. The majority of cases, at least, as a, let's say, as a general rule. But if you can add new classes, if you care about the transition between one and the other, this is a good method. Also, probably there is some interest recently about unsupervised training or retraining or stuff like that, especially from research from Meta about they say, how can we train models on the image itself, maybe something like reconstruction loss and say stuff like that, to make sure that we get a meaningful representation, so that we get a convolutional neural network that have an embedding that is meaningful for the, let's say, the task that we want to do, and not simply some random stuff that is useful for, let's say, the classification. For example, I want to show it to you an image, if I can look for it. See, let's see, in Google Images, I did get some image about that the other day. Let's see if I can find it. No, I cannot find it, but the idea, sorry, but I take Paint again. It's useful. Generally, as a rule of thumb, let's say that we are in a 2-dimensional embedding and we are doing classification. These are our axes, and here is the 0. We have a few, let's say, a few classes. Generally, this model, the softmax loss, will get embedding like that, okay? Where all the points, you should imagine this is all the embeddings for one class. This is the embeddings for another class, okay? And this is the embedding for another class. You get something like that, okay? And so you can see that if we go to look into these 2 images, no, I want the black. Where is the black? Okay, let's do like that. If you go to look in the distance between these 2 objects is very big, because the model doesn't care at all about how distant far these 2 objects are. Maybe are 2 very similar things, 2 pair of trousers of the same color, of the same brand, etc., but they're very far apart. Okay, the model doesn't care at all about that. At the same time, these and these are very close, you can see. Okay, and this is generally what you get with a classifier. Okay, at least with the classical one, the softmax classifier, etc. On the other hand, if you do something like the triplet loss, you generally get something like, okay, I was using this, you get something like this, with then maybe a somewhat similar class here and another one here, okay? And then a very dissimilar one here with another here, okay? So the distance between that, okay, the black one, the distance between inside the 2 objects inside the same cluster is not too big. And we'll try to get these two things, this side of the yellow and this side of the orange. Generally, we'll have, if you, let's say, train on much data and train well, we'll have something in common. Maybe they would be, let's say that the yellow is a t-shirt and the orange is a jumper. maybe they would be of the same color, of the same brand, or something like that. We will have something common. And the same thing can be said about stuff here or here. While things that are very dissimilar will be probably something like that, very distant, with probably the margin being something like, let's say, something that distance, let's say, somewhere a bit smaller than that. This is not true in the classification case, okay? So this is the general idea of why we want to do something like that, okay? Then there are many alternatives. There are other approaches that are, let's say, somewhat in the middle between one and the other. For example, there is a model that I remember is called magnet loss that I was interested about a few years ago, where you have, again, your observation of one class, okay? And maybe it's a bit small like that. Let's zoom a bit. And have stuff like that, many points of one class, a few points of the other, etc. Okay. And what you do is to do something like the nearest neighbor algorithm, and you try to build a, let's say, representation here, let's say an abstract point here of for this class, one for this class, and maybe also for the green. Maybe for the green you can also have two, okay? And you can iteratively update these to make sure that the green ones, the green observation are close to the green abstract points, like that, so that everyone is closer to one. And at the same time, you update the abstract point to make them sure they are representative of the points, etc., etc. And you get something similar. This is something like an alternative to this. Then also all the unsupervised methods can get some better representation. But let's say the classical classification algorithm will get you here. So the embedding will be useful for classifying that thing, but nothing else, okay? Will be very specific for that single use case. This will get an embedding that maybe is a little less good for classification in that specific case, but is a bit more, let's say, general, representative, and let's say, interesting to other stuff about that, okay? That is the general idea. So let's see if there is some other question here about the recording. I don't know. If we have supervised training with 3 classes, but can also be for other classes, can this help us? I'm not sure I understand the question. So the question is about if we train on 3 classes and then want to make prediction about 4 classes. Let's say yes, in that case, in the sense that the representation will probably, let's say, the embedding, the representation of the images would probably be easier to use for also other stuff. Okay, can similar problem be handled by knowing the silhouette score among the distinguished cluster after applying the k-means k-means? Is it possible? Yes, it's possible to use the k-means or the algorithm on that, let's say, on the embedding of the convolution network. And probably something like dbScan will work a bit better because, again, we have these elongated shape that are not generally well handled by the KNN because one dimension is much, much bigger than the other. Okay, we have again the problem that is not, the Euclidean distance was not taken into account when building this, let's say, representation. So probably dbScan will work a bit better since you will have the, let's say, closer and less closer, etc. And we will discover this shape. Well, let's say, just as an example of why this can be a problem, okay? Suppose that in that case we have 4, but let's say that we had many more. So we have many of these, okay? Since we have many classes, okay? And all of this is full. Okay, this is somewhat full. What happened when I add another representation? Another, let's say, class. It will collapse with one of them since everything is already taken. And since it's long and overlap with another class, these 2 points will be very similar, these two will be very similar, but these will be, again, very dissimilar. On the other hand, if I go to that case and I start and I put many stuff here, and I get something here in the middle, okay? Everything will be close inside, and there will be some overlap, clearly. We cannot avoid that, but probably this stuff will be similar, okay? And we're not forcing that to be closer to that one, okay? There is some, let's say, more ways to put that here without having to, let's say, occupy all that space in the radial sense, okay? So we don't have this big distance here and small here, but we have something more, let's say, proportional, where the distance is respected more, okay? Yes, some e-commerce can use this kind of stuff if they want to retrieve similar items, okay? Also, if you want to maybe, something I did in a previous work was to use this algorithm to compare the items of one brand with items of others. So we did have a, let's say, big data set of images from items of other companies, and we did look for how many of these items were similar to the one we were, let's say, considering in the past season, in the present season, to maybe get some, let's say, insight from that, and to look maybe, let's say, for example, you want to sell a new item in a store or also in a traditional store, it's the same, and you don't know anything about that item, you never sold it before, and you want to go in the past season to look at similar items to see how does it compare. Clearly, you can simply go to look into the, let's say, the category is a t-shirt and it's red, but then you can go a bit into more into the details to look if, okay, it's a red t-shirt, but is with that kind of fantasy, it's very simple or very complex, etc. You can use it to, let's say, automatically make a comparison between many different items, maybe compare one item with thousands of them without having to ask the question every time to a human expert about how similar are these two items, okay? And it can help you with, let's say, automatic that process. Okay. I think that we are getting closer to the Q&A part, but we did answer a few questions. So maybe we can take again a few minutes on the code and then answer all the final questions if we have any other later on. So let's say here we have seen more or less everything. What are other things that we can try again? Okay, let's comment this since we don't need it. Okay, let's try maybe to see how we can define the, what's the name, the triplet loss by ourselves if we don't want to use the one that is defined by the library. Okay, we can try to simply define a function. Okay, let's say that I have the X data and the, no, I will have the loss Y true and Y spread. Oh, how does it work in that case? Okay. Maybe we can simply go and look about the definition of that. we can go. Okay, to see how it will. Okay, here we have, okay, loss function. Function wrapper. Okay, that define a loss function wrapper. Okay. Okay, let's see. Let's go to see here, for example, there is the hard loss. We have the y true, the y pred, the margin. So let's define also the margin. We have the margin. Say it was something like 1, and the distance metric. Okay, I don't remember how should be put in precise embeddings. I don't remember where the embeddings are coming from, honestly, in here. Okay, now I remember, sorry. Well, what is, we have these two fields as input for our loss function. The first one, y2, is the label, the class of the observation that will tell us if the images are similar or not. Then we have the y pred, that is not really the prediction of y, but is the embedding of the images. Yeah. So the first thing that we can do is to compute the distance matrix. Let's say, for example, y pred will be of shape, this will be stage shape batch size, while this will be batch size by embedding size. Okay, we want to compute the distance matrix of that. So what we called before D2, but was simply for one example. Now we want to compute for all the batch at the same time. Okay, so I want to get something that will be of size batch size by batch size. What I can do is something like that. I reshape. I can do maybe with Keras, it's better. Keras. Okay. Expand dims. I take the y pred and I add a dimension at the end. Okay. -1. At the same time, let's say this is the first embedding. Then, and so this will be of shape batch size embedding size 1. Okay. Now I want to use the broadcasting to subtract all, make the say compute the difference for all the items. I want to get something that is like that here. You can see. So I can subtract one from the other and get all the differences, all the distance, all the differences between one element and the other. Okay. To do that, I can do something like Keras, I can transpose y pred. Okay. In that way, I get something that is of that shape. Then I can, let's say it is A1. Then I can take that again and add a dimension at the first place, 0. Okay, now we get that. And finally, I get the distance as the square of E0 minus E1. And then I have to sum across the dimension 1. sum 1. Okay, this will be of size batch size and represents the square of the Euclidean distance between all pairs of elements. Okay, so let's take for a moment the presentation and let's look at the formula. I have the distance of the positive minus the distance of a negative plus alpha, and I take only the positive part. So what I can do is to build a mask to define if any pair of items are of the same, are positive or negative. Okay, so I can build a mask, and I can do something similar using again broadcasting. Keras.expand dims ypred 0 equal keras.backend.expand dims ypred 1. Okay, you can see in that way I have added the dimension on the first axis and on the latest one. In that way I can get a matrix that check if each pair of items is equal, okay, or not. And then I can simply cast it to float, for example. So I have a float mask. Maybe we have cast, okay, cast to float X. We have casted it to float. And this is positive mask. Okay. Now, let's see how the positive mask is made. So, for example, I can try to look at this if this is working right. If I do something like Y train, I take maybe 16 elements, and then an embedding, I can make a random vector just to, let's say, look if it's working somewhat nice. Size equal 16, 32. Oh, why? Okay, close this. Okay. Positive mask, there is something. Y32. So let me look. Y, not Y red, Y2. Okay, I'm looking at the label, if the labels are equal. Okay, in this way, I get, for example, for the first elements, a mask that say if the elements are similar or not. Clearly on the diagonal, they are always similar. Okay, now let's say, for example, we want to implement like that the triplet art loss. It has done something similar in that case. It has computed the distance matrix, okay? And then here it has it has done something very similar. It has transposed the labels and checked if they are similar. So this adjacency is simply our, let's say, positive mask. And then it's done something very, let's say, similar, this logical not. So they are not similar, so they are negative, and we can do the same. So this is our negative mask. That will be not like that. Simply be 1 minus positive mask. Okay, it still works. And in fact, if we do positive mask plus negative mask, we get all ones, because either one or the other. Then what we do here is he is looking for the art negatives, okay? Because we want to compute. Okay, we have the positive. We want to find for this element 1 positive and 1 negative. I want to find something in the same way. Let's reason a bit about it. here what is doing, are positive, are negatives. Okay. How is it doing? Sorry, I'm losing a bit the reasoning. Let's see what it's doing here for completed mask minimum. Okay. Okay. Let's say that to simply do something simple, we go into looking from that element, the closer positive and the no, not the farthest positive. So we will look into the Keras backend arc max of the two axis 1. Okay, we need, okay, we are looking for the positive element that is the farthest apart. So we want to say that this will be the maximum. So if is positive, we don't care about the element itself, because clearly the element itself will have distance 0, so will be not the max. But we have to look at the element that have the maximum D2, and at the same time is positive. So times positive mask, because since this will be 0 when it's negative, this will also be 0, and this will find the index of the maximum, the element at the maximum distance. But we want max positive distance, and at the same time we want also maybe something like, since it's that is hard distance, the element that is negative, closer negative distance D2. Okay, since this is a square D. Okay, we want to look only on the elements that are negative mask. And since we want to look at the minimum, we want to take all the elements that, let's say, we want the minimum, the negative. So we want all the elements that have a negative mask. Okay. The other ones will be all 0, but this is not okay because they will get to the minimum. So maybe we can simply add a very big number, 1 times positive mask. Okay. Okay. In this way we get for each row the maximum distance of a positive element. Okay, because all the negative elements will have distance 0, and the minimum distance of a negative element, because this will get us the distance of the negative elements 0 otherwise, and all the positive elements will be a big constant number, so they will be discarded. Okay. Now we want, let's say this is something like a triplet hard loss, but we have not the guarantee that the negative will be closer than the positive. So let's say it's harder than possible, the hardest possible difference. Okay, and now we simply have to take the positive squares, the loss, the triplet loss will be the farthest positive distance minus the closer negative distance plus the margin. And then we want only to take the positive part, okay? So what we can do is Keras, activations, ReLU, okay? Since ReLU is the maximum between this value and 0, okay? And we can return the triplet loss. This is, something it doesn't like. Okay, something is table. Okay, this has type float 32. Okay, this gives us all the values for the triplet loss, and we should probably compute the average ourselves. I don't know, but let's simply try to use it instead of this loss and see if it works. No, it doesn't like it. There's something it doesn't like. Full shape received. Where is the? Why is complaining? There is some problem with the shape of something, or something like that. Let's try again. It's complaining about some shape somewhere. I don't really know, but let's say you get more or less an idea of how we define the triplet loss. We compute the matrix, the distance matrix. We find a positive mask, a negative mask, then look for a positive element that we want to take, a negative element that we want to take, and in particular their distance. And then finally we compute the triplet loss like that, okay? Now maybe I will, before sharing the code with you, I'll make sure that this works so that you can get an example of how to define a triplet loss, but I think maybe it's better now to go to answer some question, okay? So I can go to see in the questions. Okay, before applying the a priori evaluating the association rules, can we apply the triplet loss to prescribe or recommend the customer for a similar market based test? Yes, clearly we can use that this procedure to suggest a similar item, but I think probably since in let's say store something like that, we have actual information about the sales. It should be also a good idea to consider that kind of information. Nothing. Let's say we could build something like that, a model like that. I take one Python once again, Python. Paint once again. Nothing prevents us to do something like, let's say we have an image or something, again, our smile, that we want to feed to the CNN to define the vector. Something that is possible to do if we have information about, let's say, the sales of an item, is also to give let's say, tabular data like that. Let's say that here you have the sales information, the category, the price, stuff like that, the kind of information. Have let's say this is a CNN. You can have something here like a multi-layer perceptron, MLP, let's say, so standard neural network, etc. Go here and maybe merge these two together, either with a plus, with a summation of the two, or with a cat concatenation. Okay, either these two procedures to merge them together. So you can use all the data. If let's say it's probably a good idea if you want to use a Siamese neural network for so suggest the similar items, to also use some other kind of information other than the image, since you have this information, it is very valuable. So the price, the sales in the past season, some, let's say, clusterization of the customer that liked it, something like that. So there are many, also, let's say, many more information that you can feed to the model to, let's say, make it sure that the metric is even better for your task. You're not constrained to just images, okay? Always remember that. You can use both the information that you have available, and probably would be better that either one or the other. You get something that is a bit, let's say, smarter than both. Okay. Okay. I don't know if there are any more questions. If there are not, I can show maybe how we can do that, since it was the latest question. For example, if I want to, let's say, on the triplet loss, maybe I will go on my own in another moment to maybe just reason about how to implement it correctly. But let's say I open just one moment another notebook to show how we can define the network. Let's say I import all the sim libraries like that, okay? I want to define a neural network that has two inputs. This is quite simple in Keras and also in any other library. For example, let's say that I have an image of size 224, 224, 3, and tabular data of size, let's say 120. Okay, so 120 features from the tabular data, for example. I can do that. Well, I define the input, the image input, like that. Let's call it X image. And I say that the size will be 224, 224, 3. Okay. Then I have X tabular, and I say that my size will be 120. Then I define my CNN. That could be simply a pre-trained network application. See, it's that, since we already have it. I say include top false because I can say I don't want to take the prediction itself, but I want the embedding of the neural network. Okay, but I do also add another layer, since I want to average the results spatially, so that I get a one-dimensional embedding. Okay, this is my CNN. Then I want my multi-layer perceptron, that again would be a sequential model. And that's something like, maybe you should define how big you should want this net, but something like maybe relu, something like that, blah, 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 blah. Let's say something like that. I don't know how big should be, a couple of layers. Then the final layer, let's say that we want to sum the two embedding. I want to make sure that this has the same dimension. I'll put shape -1, so that this network will have the same output shape of the CNN. And then I can simply say that my prediction is equal to the CNN computed on X image plus MLP computed on the X tabular. Okay, now I define that my overall model has inputs X image and X tabular, and outputs can have more outputs if you want, but in that case, we would simply have the sum of these two, okay? And then after that, you can simply use it in that way. You say, let's go to the part of the training here. Let's say, again, we use the implemented loss. Either if we want, we simply, when this will not be, let's say, supported anymore, we can simply copy the code if we want to be sure to have it after the time, or you can find many implementation online of the triplet loss. In any case, we compile the model, and then we will make sure that our data set is, let's say, in the right format with both the image and tabular data. Okay, or otherwise we can simply say that X is that this is equal to images in this tab data, and then we have the Y, or again we have the training data set defined in the correct way. Okay. And in that way, you can also add other information. If you have, let's say, many images, many tabular data, etc., you can put all of them together simply using this other way of defining the model that is called the functional API, where you define the inputs, you define all the steps and the overall model with the inputs and the outputs. Let's see if there anything else. Okay. I don't see any other question. I don't know if you want to think about 1 minute about something else, maybe.
Everybody, this is your last chance. You can make the most of this opportunity to ask Amedeo any questions. So you can also raise your hand and I can unmute you. You can speak to Amedeo directly and pose your question.
Yeah.
Okay, we have Debashish. Yes, Debashish, you can go ahead and unmute yourself.
Yeah, thanks. Thanks, Rudha. Hi, Amedeo. This is Debashish here. Actually, the process in the triplet loss which you showed. So there, my question was related to the applying. Suppose the total volume of image, if I take and apply the even if it is a supervised image set, but still if I apply the clustering method like say k-means plus or dbscan, and priorly I find the set of centroids with the help of Similarity score, and then with the help of that Similarity score, if I further reuse it in the loss function which we are calculating as triplet, will it give better performance in case of calculating the triplet loss? Or if we directly go for the triplet loss equation which you showed, this is nothing but equivalent to calculating the Euclidean distance, that will give better result. This, if I want to compare these two scenarios, which could be the better and which could be the more accurate? That's what.
Let's say that probably there is not a universal, let's say, rule to what works better. You should probably try. If I understand correctly, you want to, let's say, use the dbscan or something like that, Kenan, to redefine the similarity to then train further with the triplet loss. Did I understand correctly?
Yes. That
okay.
was my approach actually.
Yeah, that could be a good approach if the initial definition of your similarity is not, let's say, too well defined, or maybe has some issue. Can also be an incremental approach to do that. Let's say because also in, let's say, when we have these the predefined triplet loss, we are forced to, let's say, define the classes to make sure that these can decide which are the positive and the negatives. But if we define our custom triplet loss, okay, we could also decide that we don't want to compare all the items. Let's say we can define some custom rule for the similar and dissimilar here. For example, we could, let's say that maybe we are sure, let's say I take paint once again, that is easier to explain. Let's say that we have many set of items, and we are sure that, for example, these two are dissimilar and these two are similar, but we don't want to say anything else about that, okay? So we don't know yet. We can also say maybe, okay, I'm sure about that, so please build the triplets in such a way that respect these. So these are similar, these are dissimilar, but I don't want ever to have triplets containing these other two, okay? This is simply depending on the positive and negative mask, okay? So we have, if we had an implementation that work of that, simply changing that, we can redefine that, okay? And so maybe we can start with some very, let's say, very conservative choice and putting similarity and dissimilarity only things we are very, very sure about. And then we can update also this definition and let the triplets be defined differently, okay? Again, we can maybe do some further consideration and or of any kind. For example, using some, let's say, getting the embedding and doing some something like, as you said, a clustering algorithm, something like that. And again, once we have the embedding, we can do anything we want with them. If they are good, we will be better to get better results. If they are not that good yet, the results will be less good. But again, this is possible a good idea. There is no reason it shouldn't work. We have done something similar, again, when I was working in the fashion industry, to let's say use a big data set to build a Siamese neural network, and then use the embedding with some other, let's say, algorithm. In our case, was something like decision tree, etc. Stuff like that, to get again the similarity of the items, to match, to add more, let's say, tabular data in our case. So in our case, we didn't do something like that one. We did simply train the CNN with the Siamese neural network at the triplet loss, and then we used the embedding with in a tree with the, let's say, concatenating the tabular data. But again, you can try to use the embedding in any way you want. This is, let's say, this is simply a way to build a different way to build embedding, okay? Then you can do whatever you want with it. And this is an idea could work, so it's worth to try.
Yeah, so this is a good approach, definitely. But can you please go to this live coding notebook, just left hand side tab, live coding, yeah, live coding, yeah. So here actually the positive mask and negative mask which you were basically calculating. So suppose if I do the same thing, this is Euclidean distance which we are calculating by differentiating the E0 and E1. In the other approach, suppose if I take the Y prime and Y true and simply calculate a confusion matrix, and from there if I go for plotting it with the help of heat map kind of correlation matrix. Suppose I'm calculating the correlation matrix as well. From the correlation coefficient value, if I filter it out, the highest number of correlated values in a sequential or sorted order, up to say 10 or up to 15 or up to 16, then I take those values in the correlation matrix across the diagonal, either upper half or the lower half of the diagonal. I simply put it as multiplying as say 0 to get a negative mask, and taking the lower half as the usable correlation value. Then with the help of the lower half correlation values, if I go and calculate the furthest position D2 and closest position for negative D2, then also will it fit the similar kind of result, or if we use the Keras backend, means I just want to map it with the backend cast to float function which you are utilizing here from the Keras. will that be mathematically equivalent to use in that correlation bitmap approach if I mask it manually, the upper half of the correlation matrix, and use the lower triangular part of the correlation matrix for calculating the furthest position of D2?
I'm not sure that is the, let's say, mathematically exactly the same. Let's say probably we should give some, let's say, somewhat similar results. I'm not sure. Let's say I should look a bit into more into the details to say if exactly the same. But let's say as long as you, let's say, find here a positive, a negative, and you're inside, let's say, the region where the loss is not zero, it should work. So let's say there are, let's say, you can build many possible variants, okay, of this how this could work.
Like
okay?
say all set of y true and all set of y pred if I take and pass it simply through a kind of TSNE Kullback Leibler divergence method, that kind of variance extraction, you mean to say, like TSNE or principal component analysis, dimensionality reduction kind of thing, you mean to say that where the embeddings can
let's say that probably in that case you can do the PCA, but since we are building the, let's say, the embedding, training the model, if we want to have something that respect the PCA characteristics, so the first dimension is bigger than the second one by, let's say, the variance, etc. We should try, instead of, let's say, doing the PCA afterwards, we could try directly to build that, let's say, the embedding in that way. And if we want to have an embedding of a small number of dimension, simply maybe taking the first dimension of the PCA, we should simply maybe define the embedding to be small, because again, I can simply, for example, in our model, simply go here, say I want a smaller embedding, I can put 4. I want a bigger embedding, I put 1000. So since we are building the embedding, let's say probably putting the PCA above it is adding more complexity. It could be, let's say, useful if you want to make a plot. Okay, if you want to plot the results, maybe it's useful. But otherwise, if you want to directly use it, I will put a smaller value and let let's say, the training procedure figure it out.
Okay, got it. Yeah. Thanks, Amedeo. Thanks for the nice explanation. Thank you.
You're welcome. Thank you for your question.
Okay, thanks, Debashish. All right.
Thanks, Shraddha.
Right. We will be concluding the session here. If you have any questions, please feel free to email me. I'm just writing my email address in the chat. Please feel free to drop in any questions. And as we conclude today's webinar on mastering image similarity with Siamese neural networks, we would want to extend our heartfelt gratitude to Amedeo for sharing his invaluable expertise and insights with us. We hope you found this session enriching and that you leave with a deeper understanding of Siamese neural networks and their applications in image similarity. Thank you for joining us today, and we look forward to seeing all of you in our future webinars as we continue to explore exciting frontiers of the data science field. Good night, good day, and have a great rest of the day. Thanks, Amedeo. Special thanks to you. Thanks.
Okay, thank you also to you for the space, for having this, say, this moment to talk about AI and stuff, and also thank you to all the people that participated and made questions, etc. So I will try, let's say, to share the code soon, the code and the PowerPoint, everything soon. That you can look into it and maybe hope that this will be, let's say, useful to some of you in some of your, let's say, projects. let's say, let it be work or personal, whatever. And have also a nice day. Thank you for your time.
Thanks, Amedeo. We will send over the recording as soon as it's available. And all right, thanks everyone. Thanks, Amedeo. Have a good day.
Thank you. Bye bye.
Bye.